Okay, so in this video, we're going to talk about how do we deal with diprotic acids, and then once we've sort of dealt with diprotic acids, we'll apply those principles to polyprotic acids, ones with two or more hydrogen ions that can be released. Okay, so one of the first diprotic acid students encounter is sulfuric acid, right? And in General Chemistry 1, you usually learn that sulfuric acid is a strong acid. And so hearing that, students want to write the dissociation for sulfuric acid like this, right? If it's a strong acid, it should lose both hydrogen ions, right, in a complete dissociation. The problem is, right, that's wrong, right? Students do that, and it's incorrect. What they're missing is one of the principles of being a diprotic acid. It's that the first acid proton, right, the first hydrogen ion that is released, in this case, is released as a strong acid. And so you get the hydrogen ion and the hydrogen sulfate ion in solution, right? And we write that as a complete reaction. But now the hydrogen sulfate ion is itself a potential acid. But if we look, the hydrogen sulfate ion has a Ka of 1.03 times 10 to the minus 2, right? So if it has a Ka, that means when it dissociates, it's not going to dissociate completely. It's going to dissociate to create an equilibrium. And so the second hydrogen ion comes off in equilibrium with the sulfate ion, right? And so this illustrates a principle of polyprotic acids, right? That is, right, the first acid dissociation is the strongest, and then subsequent dissociations get weaker as we go, right? So that's a principle we see in multiple polyprotic acid situations, right? The first acid dissociation is the strongest. Now, it may not always be a strong acid like with sulfuric acid, and I'll show you an example that's not here in a minute. But the first one is always the strongest dissociation. Subsequently, the dissociations become weaker and weaker acids as we proceed. Let's consider a simple explanation for that. So let's look at our, right, we've got our hydrogen ion, right, and we've got our hydrogen sulfate ion, right? I'm going to draw the Lewis structure of it here, right? And we've got that negative charge, right? So we've got something that is +1, we've got something that is -1, right? Those two are attracted to each other, right? The point is it dissociates in part because water molecules are more attracted to the hydrogen ion than the hydrogen sulfate ion is, right? So this goes off with water molecules. But let's consider this, right? One of the basic laws of physics is Coulomb's law, right? That the force of attraction between two charged objects is equal to some constant related to the medium between them times the charge on one times the charge on the other divided by the distance between them squared, right? So what we're really focusing on here is the charge part, right? The greater the charges, the greater the force of attraction, right? Well, here we've got a +1 and a -1, right, attracting each other. Now, let's consider the second dissociation. That is the hydrogen ion being dissociated in that second dissociation from the sulfate ion. Right? Here we have +1, but here we have -2. Right? So the force of attraction between the hydrogen ion and the sulfate ion, right? The force here is going to be approximately 2 times the force here. And so as a result, this hydrogen ion is less likely to leave the hydrogen sulfate ion. So here we get an equilibrium, right? This is a weaker acid, while here this was a strong acid, right? So the first dissociation was complete. The second dissociation would be an equilibrium reaction, even if we started with the hydrogen sulfate ion as our only acid. Okay, so let's consider a 0.1 molar solution of sulfuric acid, right? That's going to go into water and it's going to dissociate. So what is the concentration, or what would be the concentration of each, actually that should be in each potential species, right? If that's singular, it should be in each there. But undissociated sulfuric acid, right? The hydrogen sulfate ion, the sulfate ion, hydrogen ion, and hydroxide ion, right? We could figure out all of those things, right? Well, first, if we're taking this as a strong acid, right? So our first dissociation is sulfuric acid dissociating completely to form hydrogen ions and hydrogen sulfate ions, right? And so if we've got 0.1 molar of this and it dissociates completely, then we know we're going to end up with 0.1 molar hydrogen ions, right? Stick with our, and 0.100 molar hydrogen sulfate ions just from that dissociation, right? Okay. So let's consider the dissociation then of the hydrogen sulfate ion. So when the hydrogen sulfate ion begins to dissociate, it's going to dissociate with an equilibrium to make hydrogen ions and sulfate ions, right? We're going to start with that 0.100 molar, right? That was the result of that complete dissociation. We're going to have our 0.100 molar, that's that, and 0 for the sulfate ion. Our change will be minus x. All right, we'll go plus x. We'll go plus x here. And at equilibrium, we should have 0.100 minus x, 0.100 plus x, and x for our predicted concentrations. Okay, so we said our Ka for that second dissociation was 1.03 times 10 to the minus 2, right? And so that's going to be equal to our hydrogen ion concentration, 0.100 plus x, 0.100 minus x, right? If we work that out, you end up with a quadratic, right? Since our equilibrium constant isn't that large, equals x squared plus 0.1103x minus 1.03 times 10 to the minus 3, right? So we get that. And if we solve that, we get an x as equal to 0.00866. as the hydrogen ion, or as X, right? So now we have to consider our results, right? Our concentration of hydrogen ions is going to be this, right? Which is going to be 0.10866, right? Our concentration of hydrogen sulfate ions is going to be this, right? Which is 0.1 minus 0.00866, which is 0.09134, right? Our concentration of sulfate ions is X, and so that is just our 0.00866, right? And then we have to go back and consider significant figures and all that. But we can see that the extent of dissociation of the second hydrogen ion is much less than the dissociation of the first, which was complete, right? And so in our calculations, we can see that diminishing of acid strength as the reaction proceeds, okay? So we should be able to do that with basic diprotic acids. Here we did one where the first dissociation was a strong acid, the second dissociation was a weaker acid. Now we'll do one where both are weak, but still the first one is stronger than the second one. Okay, so let's consider malonic acid. Now, one thing to note about malonic acid here is malonic acid has two different kinds, or hydrogen ions in two different chemical environments, or hydrogen atoms, right? So there's one set of hydrogen atoms here in the middle bound to carbon, right? A carbon-hydrogen bond is not polar, or not appreciably polar. And so those hydrogen atoms feel like they are being shared with fairly. They're not going to go off to something else looking for electrons if we're considering this in the Bronsted-Lowry sense, right? While these hydrogens over here bound to oxygen, and especially bound to oxygen in this group, right, called a carboxyl group, right? The electronegativity of the oxygen and the fact that there's actually, two oxygens in this group means this hydrogen here feels unfairly treated, and so it is likely to go off looking for electrons somewhere else, making that group acidic. So here we have two acidic hydrogens and two non-acidic hydrogens. And so we can draw the formula for malonic acid like we did with acetic acid, where our formula would be something like this. H2, let me get this right, C3H2O4, where the hydrogens in front are the acidic hydrogens, and the hydrogens in the middle of the formula are the non-acidic hydrogens, right? And so that formula is telling us that malonic acid is going to act as a diprotic acid. And if we look at this, right, the Ka for the first hydrogen ion that comes off is about 1.42 times 10 to the minus 3. And the Ka for the second hydrogen that comes off is about 2.01 times 10 to the minus 6, right? And we have to remember we're dealing with negative exponents here, right? Make sure that drew correctly. And so, right, Ka1 is a number not quite 1,000 times bigger than Ka2, right? Bigger equilibrium constants mean the reaction goes farther toward products. So the first dissociation is a much stronger dissociation than the second dissociation, okay? So let's do the same kind of calculation with malonic acid that we did with sulfuric acid, right? So if we start with 0.1 molar malonic acid, what would be the concentration of all species? Well, if we write our first dissociation, right, we're going to have H2C3H2O4, right, and that's going to dissociate, and we're assuming this is in water, so I'm going to leave off the state designation. So we're going to have hydrogen ions, aqueous, plus the hydrogen malonate, right? And if we do our if we do our ice table, right, we're going to have 0.1 here, 0 here, 0 here, minus X, plus X, plus X, 0.1 minus X, X, and X. And we said our Ka for this is 1.42 times 10 to the negative 3, right? It doesn't quite meet our 1,000 folds lower than the concentration. So we're probably going to have to do the quadratic on this one. We're not going to be able to make the assumption, right? So we get our 1.42 times 10 to the minus 3 is equal to X, right? Products divided by 0.1 minus X. If you multiply that through, you get a quadratic of 0 equals X squared plus 1.42 times 10 to the minus 3X minus 1.42 times 10 to the minus 4. And if you work that out, right, take that through the quadratic, you get that X is equal to 0.0112275, keeping extra significant figures there, right? So if we use that, right, then our concentration of undissociated malonic acid is going to be equal to 0.1 minus 0.0112275, which is way too many significant figures, right? We started with 3, right? And so you're going to end up with 0.089 when you do the subtraction to the proper number of significant figures, right? Our concentration of hydrogen ions at the moment, right, is going to be equal to, because we've still got another acidic proton to consider, is going to be the 0.0112 to 3 significant figures. And our concentration of our anion is going to be the same, right? And so, right, we're partway through. We've considered our first dissociation. Okay, so now let's consider, right, we've got that information. Now let's consider our second dissociation, right? Our monohydrogen malonate ion in equilibrium with hydrogen ions and the malonate ion. Right? Again, everything is aqueous here, right? And we know that our Ka for our second dissociation is 2.01 times 10 to the minus 6. So if we set up our ice table again, right? Initial, change, equilibrium, right? Our initial concentration of our hydrogen malonate ion is 0.0112, right? You could carry more significant figures, right? We really have more than that if we need them, but we don't usually like to round in the middle of a problem, but in this case, it'll illustrate what we needed to illustrate, right? Same thing, our hydrogen ions were 0 point, right? We're not starting with 0 this time. There are some there from the first dissociation, but we haven't made any malonate ion yet. And so now we fill in our ice table, plus x, 0.0112 minus x, 0.0112 plus x, and x. But now we look and we compare, right, our value of our equilibrium constant to our initial concentration, right? Our initial concentrations, right, here and here are in the range of 1 times 10 to the minus 2. Well, this is 2 times 10 to the minus 6. 10 to the minus 2 to 10 to the minus 6 is about 10 to the 4. That's almost 10,000 difference. And so we should be able to make our assumption here, right? So we make our assumption here. We make our assumption here, right? If that x is too small to pay attention to, subtracting it from that number, it's too small to pay attention to, adding it to that number. And so when we calculate this out, we get our 2.01 times 10 to the minus 6. Our hydrogen ion concentration is 0.0112, right? We've got our x, our undissociated acid concentration, our hydrogen malonate ion is also 0.0112, right? That divided by that becomes 1, and we just get that x ends up being equal to 2.01 times 10 to the minus 6. And now we can go back in, put x in here, and we have essentially found all of our species. We know how to go from hydrogen ions to hydroxide ions and find pH and all of that stuff, right? So with these diprotic acids, right, the acid strength gets weaker, and so we can treat subsequent dissociations more and more like weaker acids and make the assumption, which makes our calculation more straightforward. Okay? So that's a little hint for working with some diprotic acids.